Yes, sir.
Okay,
Yes, sir.
okay, good. All right, so chapter 3, we're going to cover 5 things. Type of the fluid flow. So we already covered this one. Laminar flow, turbulent flow, and then flow rate, continuity of flow, Bernoulli equation, and momentum equation. So it's quite a big chapter for this one. So I'm going to break this PowerPoint file into two. So we're going to do the momentum equation first, and then no, we're going to do continuity and momentum. Okay, so first equation we look at is conservation of mass. So again, the keyword is mass. If you look at conservation of mass means what go inside the domain or system will same with what coming out. So there's no loss of mass inside there. So given by this equation, this mathematical equation, m divided by t means the rate of change of your mass is 0. So there's no change of your mass. Means your mass is constant inside the system. So the first equation for today, conservation of mass, we can write the change of mass equal 0. dm over dt equal 0. So this is the first equation. Then if we, in engineering, when we derive equation, we always start with a very, very small element. So to get the total mass, we always integrate something that is very small. So integrate with your dm, very, very small. Okay, so this is the mathematical concept. And then how you calculate the mass, you take density times volume. Okay, you take density times the volume, you get your mass. So you change the dm divided by rho and volume, because rho, there's a table that you can refer to the chemical itself. Then volume you can calculate by the size of the vessel or by the volume that defined in the question. Okay. The second law that we're going to call is second Newton law, which is F equal to ma. F equal to ma. We link up with the acceleration and mass, or you can say it's linked up with the acceleration. Okay, so given by this equation. So this equation is F equal to ma. So what is ma? In short, F equal to ma. So what is acceleration? Acceleration is the rate of change of your speed, v divided by t. So you can write m v divided by t. So you know that momentum is equal to m times the velocity. So from the equation itself, F equal to ma equal to mv divided by t, you can see that there's a momentum component inside the second Newton law. So equal to mv divided by t. So in the textbook definition, you write dp divided by t, with p equal to momentum. So it's a change of momentum over time. So again, the first law that we learn is conservation of mass. It deal with a mass. So we deal with there's no change of mass inside the system. In mathematical model, we write dm over dt equals 0. So when talk about second Newton law, you recall F equal to ma. So F equal to ma, recall the definition of acceleration. V divided by t, you combine mass and velocity, you get momentum. So then you put back into the second Newton law equation, you get the rate of change of the momentum. All right. And then you can differentiate with a very small amount of mass times the velocity. So as you can see on the screen here, the equation at the bottom of the screen here, you will see momentum equal to integration of velocity times the mass. So why we didn't integrate the velocity? Now velocity is a constant vector. inside system. So when you have a constant parameter, you don't need to integrate it. It is a constant value. So mass is a very small mass that sum up the system. That's why we write integration of V times the dm. Yeah. And recall how to get the mass. Again, mass you take density times volume. So from here, we have an equation for this module. We call it momentum equation. So momentum equation is you take velocity times times dm. So again, call what is mass. Mass is density times volume. So the combination of velocity times density times volume, you get momentum. Okay, this is an important equation for this chapter. Okay, momentum is mv. So what is m? We link up with the density, link up with the volume. Okay, so far there are three concept or three equation, maybe two. One is second Newton law, one is conservation of mass. So you're going to use these two equation to solve our problems. The next one is angular moment principle. Angular momentum, angular momentum is thing that change in the word angular. You know that momentum just now, P equal to mv. But the word angular means there is a torque, there is a twisting motion, there's an angular motion for the momentum. We define with the mathematic model here. T represent torque or twisting moment, or there's a torque moment. Torque, T represent this one, torque, equal to dH over dt of the system. So H is the angular momentum. So again, angular momentum, if you want to change something, let's say you have a system, refer to a point, and this moment was in this direction, let's say. So angular is angle, so you have a radius times the momentum here. Yeah. So again, momentum is mass times velocity. Momentum equal to mass times the velocity. So the combination of your angular momentum, you take the product of momentum times the radius vector. Okay, then you get angular of the system, angular momentum of the system. Yeah. So again, you need to link up the mass with density and volume. Okay, mass equal to density times the volume. You can expand this equation further because later on in the question for this chapter, you will focus on density and volume. Okay, so make sure you know, and also velocity also. Okay, so we just expand what we learned so far. So dm equal to rho dv. Another equation for torque can be linked up with the Fs, which is the shaft of the system. If you have a shaft, then you use the equation bottom, this one. All right. Shaft is a mechanism that turn. All right. This is a shaft. So let's say you have a blade, the propeller here is twisting. So to find the torque of the propeller here, you use this equation. Right. So the rest is just derivation of the shaft force here. So yeah. Okay. Later we will see on application, then it will make more sense here. Okay, so far we link up with conservation of mass, second Newton law, and the third one, angular moment principle. And then we link up with energy. So energy, there are two laws. First law of thermodynamics and second law of the thermodynamics. First law and second law link up with energy. Okay. So first law, it always link up with Q and W. Q is the heat transfer, the heat, and then W is the work and the energy. So energy can create heat and work. Heat and work. The difference between these two will give you energy. All right. So this is further just a recall what you learned in your thermodynamics 1. So we can write in the rate of change, which is your Q naught minus W dot equal to the change of energy inside the system. So again, recall when you have a positive value of your Q, which is your heat transfer positive value here, it means that the heat is added to the system. When your Q is positive, heat is go inside the system. Right? So W is positive when work is done by the system. Okay. So again, the positive and negative. So here you see negative means is opposite from this definition. Yeah. So this is what you learn in your thermodynamics 1. And total energy given by this integration of your small e is the energy per unit mass. Small e is energy per unit mass. Then you times the mass, you get the energy. Okay. This is E times mass. So from here, the mathematical model is the integration of your mass times the E. Again, this chapter or this module require you to link mass with another two parameter that you can measure, which is rho and volume. Okay, yeah, rho and volume to get the energy. Right. And then you have the form of the energy that consists of, you know that energy cannot be created or cannot be destroyed. It can only be transformed to different form of energy. So the first type of energy you learn in your first thermodynamic 1 is kinetic energy, potential energy, and internal energy that inside the system or the molecule itself. So we have internal energy. So the first type of energy is internal energy. Internal energy. Second one is something linked up with speed or velocity that give you the kinetic energy. The third one is due to the potential energy. Potential energy means it's fall under the effect of gravity and the height. So these three, because we use a small capital E, it means it's a per unit mass, per unit mass. If you have an E, it means all this term is divided by mass. So this one also. So this one also. This one also. Yeah. So okay. Okay, so far we link with all this general equation. Second Newton law, second thermodynamics. I'm not sure whether you already take this one too. Second thermodynamics, we link up with entropy and enthalpy. So entropy, Ts or entropy is Q divided by T. Entropy is a rate of change of your amount of heat. right? So according to second Newton law, the entropy change will always bigger than the amount of heat transfer to the system. This is a second thermodynamic law. So we can write dS over dt, which is the change of your entropy, will be bigger than your Q dot divided by T. Okay. The rest you can read from the screen. Again, we can integrate the entropy per unit mass here. The small s is per unit mass. You times the mass, you get back the entropy. So again, for this module, we will like to link the mass to density and volume. Okay, so far we cover conservation of mass, second Newton law, angular momentum, first law of thermodynamics, second law of thermodynamics. So these are the general equation that we have. So we take the first law that we learned in the first slide, conservation of mass. So we can write in this form. Okay. After rearranging our control volume, conservation of mass can arrive at this equation, consists of two components, meaning your conservation of mass referring to the first term is your control volume CV, which means we focus on volume dimension. What happened to the volume? Second term here is control surface. What I mean by control surface? Let's say we have a cube. So one cube, you have 6 faces. So it will focus on all the 6 faces. What happened to the faces? So if the mass go through the, I draw in 2D. So if the mass go out or go in through the surface, it will calculate in second term, this term under control surface. So if something, the mass go in and out, the mass go in, the mass into volume dimension, then it fall under the first term. Okay, so if you look at the equation for the first term for control volume, rho times V, you get what? Cool. If you take rho times volume, what you get? Rho times volume. What you get?
PV.
Huh?
PGV, right? PGH, sorry. Rho
No,
GH.
when you take density times volume, what you get?
Mass round.
Yes, you get mass. How you prove? Using dimension. Density is kilogram over meter cube times volume is meter cube. Cancel, you get kilogram. You get mass. Okay, so the combination of rho V, you get mass. Mass divided by time, you get m dot. Change of mass. That's why you identified the conservation of mass equation by this way. You look at the equation and then you try to do analysis based on the parameter that you look at the equation. So in this case, you take rho times volume, right? Take the volume. Rho times volume, you get mass, divided by T, you get m dot. So there's only mass here. So there will be another equation that link up with the momentum, yeah? So we look at the first equation first. The second one, if you take rho times rho times the velocity times area, what you get? You take density times velocity times area. Okay, Amir, what do you get of these three products? What do you get? Amir, are you there?
Yes, sir.
Yeah. So if you take density times velocity times area, what do you get?
Rho times V times A.
Yeah. What is the end products?
Not sure, sir.
Not sure. Okay, what is the unit of density, Amir?
You mean the units or?
What is the end products you get here?
Because the density is mass or mass over velocity,
Okay,
which
kilogram
is kilogram
over
per
meter cube.
meter cube.
Velocity,
Velocity is meter cube.
meter cube. Velocity, meter cube.
Yeah.
How you
No, no.
define
Oh,
velocity?
okay. Sorry.
Ah,
That's volume. Okay. So velocity meter square.
meter square, meter
Meter
second.
over second square.
Ah,
Meter
okay, area,
over second.
area.
Area is meter square.
So you cancel all these
Okay.
three. What you get?
Kilogram per second.
Gram per second is what? Kilogram per second is what? M dot. Yeah.
Okay.
M dot is what?
Specific mass.
Mass flow rate. It's
Yeah.
a change of your mass. So that is the question they're asking. What is the product's density times velocity times area? You'll get the change of mass inside the system.
Okay.
So that is the answer that I try to guide you. So the second one also you get m dot. So m dot in the volume plus m dot in the control surface must equal to 0. So what happened in the volume dimension must equal to what happened in the surface. Okay, so this is how you identify conservation of mass equation. Yeah, so this is the I can say the equation that you need to start remember, which is this one. Yeah, del over del t integrate of the control volume dimension rho dv plus the control surface here. Don't copy the del t. You don't need the del t for second term here. You take the rho times speed times dA. So again, this is volume. Yeah, the first term is rho times volume. Yeah. So I think when I type this one, I forget to put the center mark here. It represents volume. Yeah. Okay, so first equation you need to take home or memorize for today. Okay, so the first one is, like what I explained. The first one is on control volume, second one is through the control surface. The one that I highlight on the screen here is called continuity equation. Okay, so in exam, in test, you write this equation. you get free 1 mark, yeah, without any solution or any substitution yet. You look at the question that it asks you to solve using continuity equation, or you look at the question it asks you to solve for mass flow rate. Straight away you write this equation, right? This equation that you see on the screen, you'll get free 1 mark without further solving. Okay, again, this is how you score for this module. It's quite easy to score. All right, so we pull this equation. We have two scenarios we need to consider when you use a conservation of mass. One, when you have an incompressible float. Okay, this question I will ask Oliver. So Oliver, stand by. This question is for you. So when you have a incompressible float, let's say you consider an element. When you have an incompressible element, what happened to density? Density will go up or go down or maintain if you have a incompressible element.
Should maintain, right?
Yeah, why? Why maintain?
Because there wouldn't be any change in the structure.
Okay, so yeah, correct. Your answer is correct. You need to know how to explain, because you need to start with the density definition. Density equal to mass divided by volume divided by mass. Okay, correct. Okay, sorry, it's mass divided by volume. Right. So if it's incompressible, meaning the structure doesn't change. If you say structure doesn't change, your volume doesn't change. So the volume doesn't change, and the mass cannot go anywhere. So you're having a constant value if you have a incompressible flow. So if you look at this equation on the top of the screen here, if you have a rate of change of density, if you calculate rate of change of density over here, what do you get? If you differentiate a constant, so for example, you differentiate 100, a constant value, over time, what do you get?
0.
0, correct. So when you have an incompressible flow, your density, your first term here will become 0. You can cancel out, yeah. Okay. So you incompressible means your rho is constant. So you can another process of the mathematical model is that you factor out all the density, then you divide all the density inside the equation. So okay, there's a typo error here. They should not have this term over here. Okay, make correction, yeah. So it should not have a row over here. Okay, maybe I make correction now. And there's one more. What is this one? Okay. So you factor out all the row inside the equation. You arrive at the differentiation of the volume. Wait, something missing. Okay, I forget to copy this one. Okay, then it's correct. Okay, so you have the equation of this one. You factor out all the density. Then the first term, you arrive at del volume divided by del T plus velocity times the a, this one. So the first equation you can further reduce because the volume is constant, like what your friend just answered just now. So the first term here we can cancel. Yeah, the first term here we can cancel, become 0. You differentiate something constant with t, you get 0. So at the end, if you are considering incompressible condition, then you only left out the second term of the equation. Yeah. So in exam, if you try to solve this kind of question, first you write this equation, you get 1 mark, and then if you are looking at incompressible, you draw an arrow in your answer, you write incompressible. Equals 0. Okay, you get another mark for this arrow and all this notation. Okay, yeah, so it's very easy to score. Yeah, first you write the equation, get 1 mark, and then you look at the statement. If the equation asks you to solve incompressible scenario, straight away you go to your answer, draw an arrow, cancel arrow, write equals 0, and then at the bottom there explain why you cancel this one. You write incompressible, you will get automatic, you will get a free mark for this notation, right? And then you arrive at this simple equation. Okay. So we continue with the incompressible case that now we only arrive, we have integration of what happened to your control surface, speed times the a equals 0. Then we can calculate the volume flow rate, Q through control surface area with integration of velocity times the a. We get Q. So again, if you're not sure whether what is the parameter you get in the integration, you times them together by looking at their unit. You take volume times area. So not volume, velocity. So velocity is meter per second times area is meter square. So the product of these two, you get meter cube over second. So again, meter cube is what is volume divided by time, you get volume flow rate, the change of volume. So the change of volume in short is volume flow rate Q. So this is how you justify your answer. So this whole term, integration of velocity times the A will give you Q, will give you volume flow rate. So if you have an incompressible fluid, your continuity equation, like what you see on the screen, the top of the screen here, it will reduce up to a stage where you can calculate the volume flow rate. Okay. So if they see the question asks you to consider the fluid is incompressible, it meaning it asks you to find volume flow rate. Yeah. Okay. So you can rewrite another form for your velocity. Average velocity will be Q divided by A. This is just a rearrangement of equation. Q equal to VA. So you rearrange that one. Another scenario, just now is incompressible. Now you have another scenario. We only have two cases. One is incompressible, another one is this one. We have a steady flow. Steady means the velocity is uniform. There's no acceleration in the flow. However, you have a compressible flow. So what happened? So when the flow is steady, again, you cancel the first one because if you have a steady, the word steady itself means anything that you differentiate with time, you divide it by time, you get a constant value. right? Anything you divided by time, if you have a steady flow, you are equal to 0. So again, in exam, you look for steady. If the question say that analyze the question by assuming you are having a steady incompressible flow, straight away you write the continuity equation like that, get 1 mark. Straight away go to draw an arrow and then write steady flow, steady here, then you get another mark. So by writing equation, you scoring 2 marks already, right? So at the end, if you have the steady and compressible case, you will arrive at integration of, you only have the second term, rho v dot dA, rho v dot dA. Okay, so in this case, the rho is there. Just now in compressible, there's no rho there because you already take out the density just now. There's no rho in the equation. There's no density in the equation for incompressible. But however, if you have a compressible case, then you need to consider the density in the equation. So don't cancel out. Don't cancel out. So there's a difference between incompressible case and compressible case and steady flow. So so in this case, just remind you that we have a rho in the equation. The rho will remain. Yeah. Okay, so I think we have a short break. We will look at one or two example, then we call it a day. Okay, let me stop the recording.